Well, good morning. This is 9:34 in the morning on the 20th of October, 2016. Should be, and it's this is a Thursday morning. Should be differential equations class, and right now I'm the only one in the room. There is a book bag in the room with me, but the person disappeared, so hopefully he'll be back. We're in section 4.1, page 119, just about to start on homogeneous equations. A little bit of review what we're doing so far. We're doing linear equations, and this is also the preliminary stuff. We're looking at things, but they're showing us some possible solutions, but not telling us how to get those. So some of it's nomenclature, like we're doing here with this one, defining. So that's where we are at this point. So let's proceed with homogeneous equations. All right. A linear nth order differential equation, remember this chapter is higher order differential equations, and so far they're linear ones. Can't swear that we're going to stay with that, but for so far they are. The linear nth order differential equation has this basic form. Well, let me get my pen back to black. Okay. A sub n and I guess how I'd like to write this is y to the nth derivative of y. There it is. I knew your book bag was here and it was paying attention, but I wasn't.
At least you had somebody to talk to.
Right. Yes. All right. So let me turn on projector then.
I went down to the bookstore to see if they had the pencil that I like, because I don't know what happened to mine. So
Okay. I have
I have some, but I was trying to find
that one. Yes.
It's been spoiled.
Right. Okay.
The pencil's just
Yeah. Waiting for it to come up anyway. Okay.
Oh, I forgot.
How's your granddad?
Oh, he's here. Good enough.
Yeah. Okay. We're on page 119, section 4.1.2, kind of the bottom of the page. We're talking about higher order differential equations. That's what chapter 4 is. And the 4.1 is basically preliminary theory, linear equations, nomenclature. They're showing us some solutions, but not telling us how they got them. So let's go with this. Now, rather than writing the dnyx dn dxn, I'm just going to do it y, the nth derivative of y, like that, plus a sub n minus 1 times the y to the n minus 1. Now, see, if you didn't have parentheses there, that would be powers. In parentheses, those are derivatives, the order of the derivative. Plus, plus a 1x of x. And I've been forgetting to write that in, haven't I? Okay. These coefficients are not constant coefficients, they're functions of x. Okay? And that would be the first derivative, that I'll do the y prime, plus a0 as a function of x times y is equal to, now we're going to have that g of x equal to 0. All right? Guess what we're going to name this particular kind of higher order linear differential equation? When you set it equal to 0, they call them, what do you do to milk? Yeah, it's homogeneous, okay? So that's said to be homogeneous. Oops. Well, can't spell it, but it's there. Okay. Now, If that wasn't equal to 0, equal to some g of x like we used to do, then that's called non-homogeneous. The cream rises. No, okay. I'll try spelling it again. Okay. Now, here's some just sort of examples. 2y double prime plus 3y prime minus 5y equals 0. Now there, your coefficients are all constants, not just constant functions, but constants. Okay? Whereas x cubed y triple prime, I'm having trouble seeing that. Having trouble staying on page 2, but there it is. Plus 6y prime plus 10y is equal to e to the x. That's a non-homogeneous linear higher order differential equation. What's that?
It doesn't go 3, 2, 1,
Right,
3,
but it
1.
doesn't have to,
Okay,
because the
yeah.
a sub n of x could be 0. That's legitimate. The coefficient function could be the 0 function. So if it's a nth order, then this one can't be 0, but any of the others could.
I was just making sure it didn't skip.
Right, it can. It certainly can. And in a minute, you'll almost, I think, see why. But, okay. And here they say something I don't think I've read anywhere else. The word homogeneous in this context, oh, no, okay, I'm sorry, does not refer to coefficients that are homogeneous functions, as in section 2.5. So that's not what I was thinking it might be saying. We shall see that to solve this non-homogeneous equation, this one here, when it's equal to g of x, we must first solve the homogeneous one, and then deal with the non-homogeneous. To avoid needless repetition through the remainder of the text, we shall, as a matter of course, make the following important assumptions when you're stating definitions and theorems about linear equations, like 1. On some common interval, okay, the coefficient functions, a sub I of x, all these coefficient functions here, all those functions, the a sub i's as a function of x, and the g of x are going to be continuous. All these and g are continuous. Okay? All right. It is. It's not acting. It is bad. Okay. Now, and here's the other thing, and it was what I was saying before. Since we're assuming this is an nth order linear differential equation, since we're assuming it's in nth order, this a sub n cannot be 0. Okay, it's just like we did with polynomials. If it's an nth order polynomial, that first coefficient can't be 0. The others could, and hang on to this thought because we're going to be using this. But the first one cannot be. Any of the others could, like the second order, that coefficient was 0 on that one, as you pointed out. Okay, so it's okay there, but just not in the first one.
I guess I was thinking long division.
What's that?
I was thinking long division.
Yeah. Okay. Well, then you insert the 0 if it is 1. So yeah, exactly. All right. So that's what they're saying. That's preliminary. Now let's look at a few, a little more specific, but it's still preliminary. Differential operators. Okay, so I think I'll go to a clean page on this one. I'm sure there's a reason for them ordering things this way. I'm not going to say I like it, though. Okay. Whatever the reason is, I'm not sure I buy it.
They kind of go over a bunch of different things and then don't show you any examples until after.
Right. Okay. So here's differential operator. In calculus, differentiation is often denoted by the capital letter D. So dy dx can be represented as dy. Okay. Okay. Almost surprised it hasn't shown up in physics, but I guess maybe not. Okay. Now that I think about it, I think every one of those but it seems like I ran into it in physics before I did calculus. But you're right, I don't recall seeing it here. Maybe it was in thermal physics I ran into it. The symbol D is called the differential operator, capital D, because it transforms a differentiable function into another function. Okay, it's derivative. Okay, so if you said d of cosine 4x, I think that's what it is, isn't it? Yeah, what would that be? Negative 4 sine 4x. Absolutely. Takes one function, makes it something else. It's an operator.
So it's just the derivative.
It's the derivative. That's what it is. The derivative function. Exactly. Okay?
I mean, I guess a capital D would make sense for derivative.
Yeah. Okay. Now, it's just mathematicians are lazy. They get tired of writing all this yeah, so they just make something shorter.
No.
Let's do another one. D of 5x cubed minus 6x squared. What would that be?
15x squared minus 12x.
Got it. Okay. That's what we use them for. Now, higher order derivatives can be expressed in terms of d in the natural manner, and that would be squaring the d's. It's squaring the operators, but it's not really squaring them. It's just doing the operator twice. So
it's like taking a second derivative.
it's exactly like taking a second derivative. It is taking a second derivative. So d2y dx squared, I don't like the way they write it, so I'm doing it this way. It's the same as d by dx of dy dx. Okay, I don't know if when you did second derivatives, probably in my class, but I don't remember. Yeah. Okay. If you thought of it this way, you take the first derivative and then take the derivative with respect to x of that derivative. So that gave you d2x over dx squared. That's where that notation came from. So the d by d's are your capital D's, so that would be the same as d2y, okay? Meaning the second derivative. Yeah, that would be d of y, okay? Derivative of y. That's exactly what this says and for that. So the capital D basically stands for d by d, whatever your independent variable is, okay? Just a shorthand.
I just found it interesting. I threw a y in there now, but that makes sense.
Yeah, because you're taking it of something, okay? Like you took it of those functions up there, those were your y's, okay? And in general, your d n y d x to the n, which I was tired of writing, so I used the other notation. They are tired of writing it too, so they call this d to the n of y. Now,
And let me ask this before you continue. When you take the derivative with respect to something like y or whatever, you would have dy after it.
oh, you mean differential? Or you say after it?
When you take the derivative of something and you have like a dy left over,
Right.
is that, or what I'm trying to ask, I guess, is the y would be replaced with whatever function, right, or the equation.
Okay.
So I'm
Okay.
asking is, so would you replace the y with the 5x cubed minus 6x squared?
Yes. Okay. Yeah. Y is this function of x. Exactly. Okay.
Good. I was
And
making
this
sure
could be an F here if you wanted to call it F. That's fine too. This is the operator d by d, whatever. You have to have the independent variable here. D by d independent variable. That's what this D, capital D is. So that's why this isn't a square, no more than this was a square or that was a square. That means you just do it twice. Rather than raising it to a second power, you're just doing this operation twice. You do D the first time and then do it the next time. This one you do D n times. You know, D by D, whatever.
this one doesn't need to be in parentheses.
Yes, and that I think is the key. That before when we were doing the primes, you can do up to 3 primes, maybe 4, but then after a while you get too many primes and it's too hard to count, so you put the number in parentheses. Now I have seen, and this may be older text, but I'm almost sure of this, that at one time they used Roman numerals to represent which derivative you're doing. So 1, 2, 3, IV, D, and it's somewhere way back in antiquity. It seems like I remember seeing that before. But now they've started doing just tick, 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 and then 4, 5, 6, in parentheses. This takes off the parentheses. That's exactly what I was going to say next. This just tells you how many times you're doing that operator. Remember, this is an operator, not a function, but they sort of act like functions.
The only thing I'm sad about now is we don't have anything.
All right. Well, those up there were sort of little examples. Okay. Now, there is a reason for this too that they're doing. I know what they're heading at, but you could have done it without it, but it's fine to do it. Where y represents a sufficiently differentiable function. In other words, if y is a differentiable function, this nomenclature makes no sense. If you can't take the derivative, no reason to put d's in front of it. Okay. Now, polynomial expressions involving d, such as d plus 3, that also can operate on that function y, or f, or whatever you want to call it. That would be dy plus 3y. Okay? In other words, derivative of y with respect to x plus 3y. That could do there. Notice, that 3 is a real number. That is an operator. An operator. Okay? So you could have higher orders of those, like d squared. This is really getting bizarre. Plus 3d plus 4 is minus 4. Okay? And that could be operating on some function f or something else. And that would be the second derivative of that function f plus 3 times the derivative of that function f minus 4 times f. Okay, and here's Victor. And you just happen to come to the wrong class. You're in the linear algebra. I put you in differential equations. Not always, most of the time. But yeah, okay. All right.
Just know I'm going to stick around.
Yeah, you better, because I already marked that way. Okay. So, these are ways of expressing this, okay? They can keep going on and on and on. I don't know if it's beneficial to, but since they write them in the book, I'll write them here too. Here's another. We're talking about an operator. Capital D stands for the operator, d by d, whatever your independent variable is. That's an operator. Mathematicians are just basically lazy. They get tired of writing d by dx, so they write capital D instead. Okay? And then they start combining them with other things, like even this, 5x cubed. Is that it? I can't read. Yeah. D cubed. Now, it doesn't have to be the same power, but this one just happens to be. minus, oh boy, they are doing that, minus 6x squared d2. Yeah. I don't like to call that squared and cubed. I call it d2, okay, plus 4xd.
Yeah, because it's not really squared, it's just second.
Right, okay, plus 9, okay. That's an operator that could act on some function. Let's call it g or some other function. Probably. Yeah, it's got to act on something. It's an operator that has to act on something. If you ever get into quantum mechanics, they have all kinds of operators, Hermitians and Hamiltonians, and yeah, and quantum mechanics are crazy people, you know. I think they have this one operator. See if I can remember. It seems like they use the symbol this and that, like we do for vectors. Yeah, but they use that symbol for another operation. And actually, something goes in here, and then you put a bar, and something goes in here. Yeah, okay. And this is just how crazy physicists can be sometimes. They needed a name for this operator. And this says, and here's the deal. This can operate B on A onto B, or it can go this way too, operate B onto A.
Almost like a
yeah. All right. So they needed a name for this. It does a certain thing. It's an operator. So they named this the bra operator, and that the ket operator. Together they make a bracket. Literally, you bra this and you ket that. And they literally, I'm not making this up, they use those as operators.
I think physicists can be lazy.
They can be extraordinarily lazy. Okay, so we won't call any names. Okay, so you lose. Okay. I can't get the eraser to erase. There we go. I guess I don't hold it down long enough or something. Okay. And by the way, then that would be, this translation would be 5x cubed times the third derivative of g minus 6x squared times the second derivative of g plus 4x times d by dx of g plus 9g. Okay.
It can get pretty hairy.
It can, and
Especially if g is like a trinomial or something.
yeah, you mean expand that into bigger functions, polynomials. I'm trying to think if I've seen them do that. I can't recall that they have, but anyway. But those are also differential operators. In general, we define the nth order differential operator or a polynomial operator to be, and here they throw in another symbol, and it actually becomes an operator itself, okay, and that's L. Now, most of the time, the capital L is used as a linear operator, so I don't think it's any accident that we're using L here, since we're dealing with linear differential equations, higher order linear differential equations. So, for instance, that could be, here's an operator defined by operators, okay? L would be a sub n of x, and like you said, that now can be any function of x, polynomial functions, exponential functions, trig functions, any log functions, and combinations of those functions of x, d to the nth, except that's not to the n, I call it dn, plus some other coefficient function, n minus 1 of x, and that goes with the operator that's the n minus first differential operator plus, and then you dot, 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 all the way down to, say, your A1 of x. You could start anywhere, but D plus A0 of x. Okay, and that's the operator. Okay? You operate on the function y, alpha of x, whatever that phi, whatever that function would happen to be with that operator, and that combination makes another one, and this is a linear operator, okay, because all these differentials are to the first power. Okay, so that's our equation 8 they're going to refer to later probably. As a consequence of the two basic properties of differentiation, I'll get this one, let's forget about the L for a moment here, and D of operating on C f of x, okay, what's that? Oh, sorry, okay, yeah, I want to make sure I was doing it the same way they did. No, yeah, you can pull the constant outside the D, okay?
So the C times D of f.
That's it, exactly. What I was starting to say, and then I regretted the fact I called that L a linear operator, because this thing that we're doing now is one of the two tests of linear operations that you can take the C outside the operator, and that would be operating on f of x. Now before I've just been calling that f, they're putting f of x. It doesn't matter. Okay. Now, here is the second feature of a linear operator, is D operating on the f of x plus g of x is D operating on f of x plus D operating on g of x.
It follows some general rules that we've seen before.
General rules of linear operators. And that's exactly what it is. It is a linear operator, even though it's taking a derivative. You take derivatives of functions this way, and that's true. When you take the derivative of a constant times a function, you pull the constant outside. Okay, so this is just so therefore, and this is what they're getting at. And I would have waited till now to introduce that L. They did it before they told you these two things, but that now makes this a linear operator, because this thing is all operating on some function L for G, or some combination of L for G, and that operates on this just like this. You can operate on the function here and here and here and here, you know, or you can take this A of X outside and then, you know, so it fits these two criteria, that those are true. So that is a linear operator, and that's why I said usually refer to it, and that's what they are. Now they're telling you that's why they named it. Why didn't they do the other two first and then introduce the L? I don't know. Okay. So here's the generic way of combining those two into one. Okay. L operating on alpha f of x plus beta g of x. See, this is going to combine both of them together. That is the same as alpha operating on L of f of x plus beta operating on L of g of x. So that combines the additive and the multiplicative, the constant, together. Okay. And if we can show that an operator or a function obeys this, like that, then it's a linear operator or a linear function or a linear whatever we're dealing with. I think those are the only two things we'll be dealing with. Now, why all that? Now, this is all background stuff before what we're really going to get to. Okay? Differential operators. And the thing that bugs me a little bit about this, I think it would be better to call these derivative operators. Because we think of the differential as when you split the derivative and have the d on one thing and d on the other thing separated. But these are differential equations which can have derivatives in them, so that's why they're allowed to call differential operators. I don't know why they didn't call them derivative operators, because that's what they're doing. They're represented various things as derivatives. But I guess differential is just a smoother word or something. So now let's look at differential equations. I thought that's what the whole book was about. Okay. Any linear differential equation can be expressed in terms of the denotation. So there's a part of me that said, why did we introduce this way back at the beginning? Why did we wait till now?
This is what we've been waiting for.
Yeah, I guess. Y double prime, this is how I started writing because I got tired of writing the DVDs, plus 5y prime plus 6y is equal to 5x minus 3. Okay? Can be written this way. How would you write it? Using differential operator. D2 plus 5d1. Yeah, you don't have to write the 1. I wrote it because you said it. But okay. Okay. Plus what? Plus 6. Okay. Yeah, separate that out. I want to make sure I do it the same way they did. Well, what they did is write the y's after each of them the first time. What I was going to do was this, which is the same as what they did. In fact, they did it in the next step. Is equal to 5x minus 3. Okay, what they were saying, this is d2y plus 5dy plus 6y equal 5x minus 3. And then pull out the operators.
That's what you're operating on.
That you're operating on the y. And because you're operating on the y and not some power of y or some power of the operator of y, this is a linear operator. So that's where we use them, how I will use them. So actually this goes to this goes to that. Okay. But notice the g over there, the 5x minus 3, doesn't get operated on. That's separate. Okay? And now, for the life of me, I don't know why they do the L. Okay? I so far don't see any advantage of it, except, again, it makes it shorter to write. If you define this to be the L, then you can say L of y, okay, and they do put it in parentheses, equals 0 is the homogeneous case, and L of y equal 5x minus 3 is the, and they haven't quite said it yet, but I think they'll call that the general case. I hope I'm using that word correctly. I think that's what they call the general case, or a specific case, or something. They call it a separate case. The non-homogeneous case. Okay. Non-homogeneous case. But later we're going to shorten that and use a simpler word than non-homogeneous. Okay. All right. Now, that said, we go to a different, but building onto a different process, the superposition principle. Okay? The sum or superposition of two or more solutions of a homogeneous linear differential equation is also a solution. And this is your theorem 412, and since I know you don't have a book, let me write this down for you. Sorry, I'm clogging up again. Superposition principle. Second?
It's just got to be cold air.
Yeah, I'm pretty sure that's what it is. We're going to code y1, y2, 2, and they keep counting up to y sub k. I had to make sure I was going to use the same subscript they did. Huh? Well, they used n earlier to represent the power, which derivative you're using, so they didn't want to use n to confuse it, and yk, I don't know. They just put some letter. I know you've done some programming, and they probably aren't as picky about this as they used to be, but originally in programming, the letters I, J, K, L, M, N, I think it stopped with N, were, unless identified otherwise, were always integers. And any other letter, X, Y, G, Z, A, B, C, was assumed to be a variable, or represent any real number. So that's why it's typical for them to subscript a counter that's just counting. Which of these are you talking about? A sub n minus 1. They almost always use one of those letters, I, J, K, and just like I, J, K, I, J, K, L, M, N. Those were reserved to be integers and generally positive integers unless you noted otherwise. And every other letter was assumed to be a floating decimal. That's technically how they call it, a floating decimal, not an integer. Not necessarily an integer. Could be, but generally a floating decimal. And literally, when they did, got them into, I'm sure when they translated them into light on, light off, ones and zeros type thing, that was specified by those letters, okay? That if it was only an integer, you didn't have to have decimal point, you didn't have to have powers, you didn't have to have anything else because of the way they represented them. So K was just one of those counters. I call them counters sometimes. They use just to count things, 1, 2, 3, 4, 5, integers. Okay. YK, I don't know, except they didn't want to use N. Why not I don't know. J, I don't know. But, okay. So let those be solutions of the homogeneous nth order DEQ. Let's see, what is DEQ? Differential equation. I can't remember if they usually write that capitalized or lowercase. What's that? Okay, that's what I did. It just seemed better that way. Okay. Differential equation.
At least I know I've seen DE.
Yeah. And that's probably what it is, DE. That's what they do, differential equations. They don't, sometime in my ancient past they did DEQs, but now they just say DEs. That's right. I remember now. Okay. On some interval I. Okay? Then the linear combination y is equal to, now this is a generic y, not one of those other y's, sum c1 y1 of x plus c2 y2 of x plus ... plus ck yk of x is also a solution, where the CI, and again, okay, a counter integer where I is going from 1 to K, okay? That's probably why they didn't use I. They wanted to use I here, okay? Still don't know why they didn't use a J, but whatever. These C's are arbitrary constants, okay? That's also a solution. So in other words, if you have a homogeneous nth order differential equation, and you know that these are solutions for that, then the sum of those solutions is that, with C being not just sum of solutions, sum of multiples of the solution is also a solution. And that's called the superposition principle. Now, y'all have had physics, right? You've had physics too, right? Okay. Remember, waves follow superposition principles. You know, and you may not have hit this, but if this is a wave and that's a wave, then you let the waves combine and you get a superimposed wave.
Either they get larger if they're like in the same direction, they get larger.
Right.
If they're opposite, they go nothing.
Right. Or yeah, exactly. They could constructive interference or destructive interference, and that's superposition. This is not quite the same concept, but they use the same term for it. Okay. They proved the case here for L is equal to 2. I'm sorry, K equal to, with L being a differential operator. And you can see, because it's a differential operator, it obeys that rule for linearity. Because it's a linear differential operator, it obeys that, so that now instead of alpha and beta, you have C1 and C2, and your solutions are Y1 and Y2 rather than F and G, but it's the same thing we just did. And but the interesting thing, because it's a homogeneous differential equation, the L of Y is equal to 0. So if any of those L of Y's is 0, L of Y1 or L of Y2, doesn't matter what the constants are, constant times 0, yeah, it's still going to be 0. Okay.
That's
now,
not an easy proof.
yeah. Then the corollary to this theorem, here's the A corollary. A constant multiple, Y is equal to C1 of Y1 of X, okay, is also a solution, where Y1 is a solution, okay, of a homogeneous differential equation. The C1 is also a solution. I mean, that just comes from, if all the other C's, they could be arbitrary, were 0, then this certainly has to be true, as long as that C was not 0. And then the B part is the homogeneous linear differential equation always possesses the trivial solution Y is equal to 0.
It's all about the trivial.
Right, we've done that already, so there's nothing new there. But if that thing is equal to 0, that differential equation is equal to 0, then Y is equal to 0, its first derivative is equal to 0. So all those higher order derivatives are 0, and all the sum of that is going to be 0. So every one of them that you had, it would be 0. Okay. So that's usually where we start, but they throw this in at the very end here. Finally, now, you want an example, you get an example, okay? Whether it's going to be what you were expecting, I don't know. And again, they don't tell you how they got these, but they got them. The function y1 is equal to x squared. y2 is equal to x squared log x. Okay? It claims here they're both solutions for this homogeneous linear equation, x cubed y triple prime minus 2x y prime plus 4x, no, I mean, sorry, 4y. It's going to say you can't have that without a y in it. Okay. I misread it. 4y is equal to 0. Okay? Now, first, that is a linear, homogeneous, higher order differential equation.
It's on an interval.
Oh, and it also has an interval. Okay, sorry about that.
From 0 to
Where is it? On the interval 0 to infinity.
didn't let you go on with that.
Okay, yeah. It is a, it says all the things. All the y's and derivatives of y's are to the first power. Okay, no squares in there. Y double prime squared or y prime cubed or y squared or y to the 1/3, 3/2 or anything else. They're all linear in y's and its derivatives. Now, the functions don't have to be, okay? Not at all. Okay. Now, they claim, okay. Now, obviously here, hopefully you'll see this. You couldn't have 0 in the domain. No problem here, no problem here, here. Big problem here, okay? X can't be 0 and can't be negative. You can't take the ln, the log of a negative number, and you can't take the log of 0. So that's the main reason the interval is restricted there. For any value x beyond 0, positive value x beyond 0, that works. And here's Ashley. All right. Now, I'm trying to recall, did you get a copy of the first test? Huh? Cal 3. How about for linear, for either of these two courses? Okay. Before I forget it, because I should have gotten it to you sooner, but let me make sure you got it now. Victor, you got it, right? Okay. There you go. And you want the other one too? I got your papers, and I can't remember if I got the grade on the blackboard yet, but if not, okay, now we've actually had 2 tests in linear algebra. Did you get either one of them? Okay. Here's the first. I did give you the second already, right? Okay. Sorry about this. Somewhere back here. There it is. Now make sure those are both, you got 2 different pages, because I happened to notice this one had first page, second page. So, okay. All right, there you go. Okay. We're on example 4 in chapter 4. Section 4.1, chapter 4. It's the superposition homogeneous differential equation, DE. There it is. I see it. Okay. Now, they told us these two are solutions to it. Do you believe them? Or do you want to verify that?
So you put those dashes, it looks like they're negative.
Okay, sorry about that. Okay. They're telling us those are solutions. Do you want to verify that or not? It's up to you. It's not that hard to do, but just asking if you want to do it. Huh? You can believe it. Okay. Do y'all want to see it verified just to remind yourselves how to verify or not? Okay. All right, what we would do then is start with y1 and do y1. We know what that is, so let's do y1 squared. What would that be? First derivative of y1 would be 2x. Second derivative of y1 would be 2. third derivative of y1
0.
would be 0. Let's do the same thing for y2. y2 prime would be, do I really want to do this? Okay, what would that be?
2x
2x
over
log x.
log x.
Yeah. Product rule. Glad we're doing it. Okay. Plus,
Plus 1 over x. Right?
yeah, 1 over x times x squared, which would just be x, right? Okay. y2 double prime would be, you tell me.
Another product rule.
Yep.
So you got 2
2
natural log of x
log x plus
2x
times 1 over x, which would just be 2 plus, second, 1. Okay, so this would be 2 log x. wait. Yeah, 2 log x plus 3, right?
Yeah.
Okay. And your y triple prime, y2 triple prime would be,
It'd be 2 over x.
2 over x. Done. All right. Now, I probably should have done each of these separately, but let's do x cubed y1 triple prime, 0, minus 2x times 2, that would be minus 4x, right?
Right.
Okay. Plus 4 times y, which is 2x.
I thought it was x squared.
Oh, I'm sorry. I did look at the wrong thing. X squared. Okay, you're right. Up there. And the question is this equal to 0? This will be, oh, I messed up. This is 2x. I put the wrong one in. It's plus 2x. Let me back up. I had forgotten that they skipped a term here. Had not noted it. It's minus 2x times y prime, which is 2x. And that's minus 4x squared plus 4x squared, sure enough, is equal to 0. So that one fits. Let's see if the other one does. Okay, let's try to get it right this time. X cubed y triple prime, which would be 2 over x.
So it'd be 2x squared.
I'm sorry?
Wouldn't that be 2x squared? Like, I mean,
Oh, yeah, right. Once you do that, yeah, okay. I was just going to take it one step at a time rather than skipping 2 minutes. So that's 2x squared. You're absolutely right. Minus 2x times y prime, which is 2x. No. Sorry, I looked at the 2 right. I'm not going to get it right, am I? Okay. Yeah. It's a lot bigger thing. Okay. It's this one, okay? And that would be 2x times 2x log x plus x, right? Okay. Plus 4 times x squared log x. All right. We already did the first one, that's 2x squared. Minus, and here we have a 4x squared log x minus 2x squared, distributing across there, plus 4x squared log x. These add to 0, those add to 0. Sure enough, that equals 0. So yes, both of those are solutions for that linear differential equation.
That's how we check.
Second?
That's how we check.
That's how we check.
But not how
Now, that gives you a y1 and a y2. This is a third order. I'm jumping ahead now. There is another solution. So, of course, we know what that is, don't we?
Zero.
The trivial solution, that y is equal to 0, because then 4y would be equal to 0, y prime would be equal to 0, 2x and y prime would be equal to 0, y triple prime would be equal to 0. So, yeah. So we know there's at least those three. Okay. You don't need to do any more, but just letting you know there is another one at least. Okay. Now, that was all showing that what they said was true. You wanted to believe them anyway, and you were right. They aren't going to often lie to you. Okay? Okay. We hope not anyway. So those are...
There's a lot of things we got to learn.
Right. All right. All that was just to verify. But since I wouldn't be surprised if you might not need to verify something sometime, I thought that every opportunity to verify probably was not a bad.
That and if we don't have a whole lot of opportunities for examples.
Right. Sometimes.
So, next page.
Yeah, we'll get a bunch of them, I think. Okay. Now, they told us those were both solutions. We just verified it. By the superposition principle, what would be another solution? In fact, sort of the general solution. Y is equal to... No, okay, yeah. You could do that, but...
Oh, you said general.
Yeah, okay. C1...
You said trivial.
Okay, oh, okay, I said, yeah, general. X squared plus C2 x squared log x. Since both of those are solutions, we verified they were, then you can use superposition principle, multiplying those by arbitrary constants and adding them together. That's also a solution. Okay? That's superposition principle. Now, that's all there is to that one. I mean, that's not really much of an example.
There's some more stuff below.
There's some more stuff below it, but that's a different problem. Here's another, and I'm trying to see, I think I want to start a new page on it just so it won't be confused, okay, with the other. Here's another y equal e to the 7x, and they say that is a solution for y double prime, is that double, yeah, minus 9y prime plus 14y equals 0. Another homogeneous equation. We know that, we know there's one, the trivial, and here's, they claim is another one. Okay? Now, let's quickly verify this too. What's y prime? 7e to the 7x. And y double prime is 49e to the 7x. Now let's see if 49e to the 7x minus 9 times 7e to the 7x plus 14 times e to the 7x, is that equal to 0? 49e to the 7x minus 63e to the 7x plus 14e to the 7x. I know e to the 7x will never equal 0. The question is 49 plus 14, that sure enough is 63 minus 63. Yep, that's equal to 0. Now, you didn't need to verify it, but I just wanted to get you. So, indeed, that is a solution. Now, what they're claiming here, and it's absolutely true by that first part of the corollary up there, is any multiple of that. Y is equal to C e to the 7x is also a solution. Because all you have to do is take the derivatives again, you get a c there, you get a c here, you get a c here, multiply all those together, factor out the c's, yeah, still 14 times. It's going to work. So, that's also a solution. And by the way, when c is equal to 0, that does give you the trivial solution. So it does. But any c, positive c's, negative c's, fractional c's, decimal c's, rational c's, irrational c's, we're going to stay in real numbers, but they're all solutions. They show 9, 0, and negative square root of 5. Any c value will give it. New topic, okay? Linear dependence and linear independence. All right? Definition coming up. And I know, yuck. What's that? Yeah, we sort of seen that somewhere before, haven't we? Or if not, we're going to. How much time do we have? I'm trying to figure out if I'm going to make it without clearing my head or not.
It's 10:36, so we got 10 minutes.
Oh yeah, I think I can make it. Okay. Here's our definition 4.1.1. Okay. Linear dependence and independence. A set of functions, f1 of x, f2 of x, f3 of x, I'll put one more than they did, dot, 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 up to, now they're using n, okay, fn of x. Those are just counters, okay? That's why they use integers. They're said to be linearly dependent on an interval I, okay, if there exists constants c1, c2, dot, 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 up to c sub n, okay, not all 0, okay, that's an O, not a 0, it's in the word 0, but, well, okay. I don't need to slash my O's. I only slash zeros. Such that, yeah, C1 F1 of X plus C2 F2 of X plus dot, 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 plus Cn Fn of X is equal to 0. Okay? Now, it's linearly independent if you can come up with some C's, as long as they're all not 0. Certainly, if they're all zeros, that's going to produce 0. So we don't want all the C's to be 0. But any selection of zeros that could make the sum of those functions equal to 0, then we say that's linearly dependent. In other words, there's some function in there that is a combination of all the other functions, so all you have to do is negate it and you wipe out all the others. So that's called linearly dependent. If there is a set of C's, not all 0, that makes that true. For every x in the interval, for all x in I. Okay. If the set of functions is not linearly dependent, then it's linearly independent. That's pretty clever, isn't it? Okay. Now, what does that mean? If you cannot come up with a set of C's, not all zeros, and get that equal to 0, or the other way of saying that, if the only set of C's that you can use to combine those functions together in this linear fashion, the only way you can get that to be 0 if every one of those C's is 0, then we've said that's a linearly independent set. So, if you say let's go to vectors here, some vector here, going up through space here, that's some combination of x, y, and z. And those are linearly independent of each other. You can't replace this x with some combination of y and z. It's never going to go this direction. Okay, so those are linearly independent of each other. But if you use the plane here and you use some x, y, and then some other function here, well, that vector here on the plane can be made up of some combination of these two. So therefore, those three are not linearly independent. The three, okay. Now, obviously, those are. There are others that don't have to be orthogonal or other things that would be linearly independent. But that's just an example you're probably used to seeing, whether you've ever thought of them that way or not. So in other words, a set of functions is linearly independent on an interval I if the only, I've already said that, the only constants for which that combination, that linear combination, is equal to 0 is if every c is equal to 0. Okay? I almost want to call that the trivial case, but we don't. Okay? Not just so we don't confuse it. It is easy to understand these definitions for a set consisting of two functions, f1 of x and f2 of x. If the set of functions is linearly dependent on an interval, then there exists some constant c1 and c2, both not 0, for which every x on the interval c1 f of x plus c2 f2 of x is equal to 0. This, to me, is a lot of blah, blah, blah. I mean, they're saying the same thing over and over and over. Therefore, if we assume that c1 is not equal to 0, then it follows that f1 of x is... All right.
We probably just skip down the road and start talking about sine.
What's that?
We probably just skip down the road and start talking about sine.
Yeah, well, I think there is something of value in what they're saying here. It's just taking a long way to get around to it. Okay. If the set of functions is linearly dependent on an interval, then we say that c1 f1 of x plus c2 f2 of x equals 0. If they're dependent, then there are c1s and c2s, not other than 0, that make that true. So let's assume that c1 is not equal to 0. That's what they're doing. c1 not equal to 0. If we said this is linearly dependent, if that's what's given, then we can assume c1 is not 0. If that's the case, then we can divide by c1, right? Okay? So, and I'm also going to move to the other side. So then this would be f1 of x is equal to minus c2 f2 of x, that's when subtracted to the other side, divided by c1. c1 not being 0. Okay? Well, now, this shows that f1 and f2 depend on each other. One is a scale, minus c1 over c2, whatever signs and values they have. You know c1 is not 0. Basically, it's saying f1 is just a multiple of f2. Okay. Some multiple of f2. So if you're in, if this was f1, then f2 could be this, or it could be that, or it could be that, but it's some right now. If it's
It would be parallel if it was a vector.
I think it has to be collinear. I don't think it can be.
Same.
Yeah. If it was parallel, I think that is technically the no solution case.
Gotcha.
This would be all solution case. I mean,
Also, yeah. And then
infinite solution case. Not all, infinite
The
solution.
argument will be something we're going to get to.
Yeah, we're going to get there in just a bit. Okay. Well, hopefully. Okay. Maybe not today.
Because we're out of time.
Are we out now? Okay. Well, we didn't get very far on that, did we? But I think we took care of that first part. That is, if a set of two functions is linearly dependent, then one function is simply a constant multiple of the other. That's what we just showed. Okay. Conversely, if F1 equals C2 of F2, okay, we'll maybe begin there next time. All right.
There's just so much nomenclature.
There is, and it's so
It boxes
boring. Why don't we just get to the thing? I think that's what I liked about the one I had when I was an undergraduate. The text cut through all this stuff, and we went right to, let's see how these things
I think
work.
what they're trying to do is establish a solid base of knowledge so we know what's going on. But
Yeah.
it's kind of
But it's sort of like,
so much is going
it's
on.
like learning vocabulary of another language, but never putting a sentence together. I mean, by the time I get to, okay, let's put a sentence together, I've forgotten the vocabulary. Okay, so, yeah, so I don't know. I shouldn't be griping, but I am. Okay.
That's pretty accurate.
Exercise set 4.1. I think you can do 1 or 3. Think you can do 5. Okay, stop there because now they're talking about general solutions, and I don't think we've introduced that nomenclature yet. Yeah, that's coming up in theorem 4.1.5, so that's coming up a little bit later. So we went through a lot of pages, but didn't get a lot. Well, I don't know. Not fair. Anyway, we'll see you on Tuesday. Okay, you on Monday. Okay, but and you on Monday. All three of no. Yeah, all three. This is my Monday class too. Okay.
Are you sticking with your algebra?
Yeah.
So we'll see
Yeah.
you in about 5 minutes.
Yes. May keep seeing you. Okay. So let me end this.